Okay, so now we're going to be discussing about first-order linear differential equations. This one is the one that has the most general form that we can maybe use when we're talking about circuits. So first-order linear differential equation is given by the following form: dy dx plus some function p of x, y, equals to q of x. Now, q of x can either be 0, in which case we call it homogeneous, or if it's not 0, then it's going to be called non-homogeneous. So in this situation, we're going to assume that this is in general not homogeneous. Now, we want to solve for y. Y is equal to something. But we can't do that directly because we can't separate it, we can't move it to the other side and then factor. So, as such, we are going to assume the following. First, notice on the left-hand side, it looks something like f prime g plus g prime f. And if you notice, this is just the following, it's just a derivative of the product rule. So our intention is to then make it so that we can have the following. So I'm going to multiply something called I. I is our integration factor. So that we have the following: I prime y plus I y prime. So first, I multiply I to both sides. I dy dx plus I p of x y equals to I q of x. I'm going to then relate only the left-hand side to this. So we have di dx y plus I dy dx equal to I dy dx plus I p of x y. Notice this part we can cancel out, and we can solve for I directly. Notice that this is just a separable differential equation. I p of x y, and we can get rid of the y as well. And then we can separate. So as such, we have di dx, di divided by I equals to p of x dx. In order to solve for I, we just integrate both sides. So over here, we get the natural log of I equals to the integral of p of x dx. Now, unfortunately, we don't have a simplification for the right-hand side, mainly because we don't actually know what p of x is. So, as such, we keep it like so. Now, we can then solve for I by assuming that I is greater than 0. As such, we're able to then take the exponential to both sides, and so I is equal to e to the integral of p of x dx. However, I don't really like this form, so I like to express it as the exponential of the integral of p of x dx. So, just to recap, we're given a form dy dx plus p of x y equals to q of x. But in order to simplify, we have to multiply the integration constant I to both sides. When we do so, we break this down into d dx of I of y equals to iq of x. From here, we're able to integrate both sides with respect to x, and we get that iy is equal to the integral of iq of x dx. Now, One thing we have to do first is solve for it. So as a placeholder, I would say this is answer 1 plus c. To finally solve for y, we have answer 1 plus c divided by I. And that's our result. Now, to enumerate the steps, given dy dx plus p of x y equals to q of x. Number 1, check the form. Check form. If it's matching the form given above, we move on. Number 2, check p of x. What is p of x? It's usually given in the problem. Number 3, we find our integration factor, which is given by the following. Number 4, simplify down to d dx of I of y equals to iq of x. And then number 5, find iy equals to the integral of iq of x dx, which is equal to some answer 1 plus c. Then finally, 6, y is equal to answer 1 plus c divided by I. And with these steps, we're able to solve any kind of first-order linear differential equation given that form. So in the next video, we're going to be doing 2 problems regarding first-order linear differential equation. Okay, thank you.